Okay, so today we're going to talk about gas laws. So I'm just going to introduce the concept of gas laws, talk about them briefly, and then we'll get into the actual gas laws in a little bit. So gas law, what we mean by gas law, is it's a generalization, just a way to describe, in mathematical terms, the relationships between amount, pressure, temperature, and volume. So we're going to have four variables possible variables in a gas law. Some will have some and not others. And so we've previously discussed temperature, amount, and volume. So let me make sure I'm totally clear on that. So temperature is going to be just T, temperature. Volume is V. Let me explain what I mean by amount. In amount, we're going to be referring to amount in terms of moles. So moles, and the variable for moles is going to be N. It's because M was already taken with mass, and we started having to use other weird letters. So N is moles. The only one of these we haven't really talked about ever before is the idea of pressure. So let's talk about pressure. I'm going to give you a couple different definitions, because there's a couple different ways to think about pressure. But they all kind of fall under they all work together, but one of them is a little weird, and the other makes, much more sense, I think. Pressure is force per unit area. So the mathematical equation, which I'm never going to actually require you to, use, is force over an area. So, what am I trying to say? So we experience this a lot of times, is that general idea of force divided by area is pressure. So, this is why knives are good at cutting, right? Because they take the certain amount of force that you're putting on the knife, and they divide it over a very small area. That's what we mean by a knife being sharp. Another way to think about this is if I'm doing push-ups or something, and I'm using my entire hand, right? I'm dividing the weight that I'm putting on them, the force that I'm putting on them, over my whole hand. But if I then try to switch and just use my knuckles, it hurts more because I'm putting the same amount of force over a smaller area. And if this goes down, then this goes up, and the pressure is higher. So this is why a knife cuts you. This is why doing push-ups with your knuckles hurts more. Another application you may have seen is, everyone can fairly well figure out if you were to step on a nail, right? It would hurt you. It would hurt it'd go into your foot. But maybe you guys have seen this thing where people lay on a bed of nails. I hate to, maybe some of you realize this already, but it's a trick. It's totally a trick. If you have a whole bunch of nails of exactly the same, right, height, which I didn't draw here, same height, right, they all are even with each other, and you have thousands of these things, you may not think of it, but there is a little bit of an area here. There is a certain amount of area for each nail point. Now, the reason when you step on a nail that it goes into your foot is because there's a certain force over a very small area. But if I were to take my body weight, instead of putting it all on my foot and all on one nail, I divide it up over hundreds or thousands of nails. Now I am increasing the area over which I am distributing the force of my weight. Weight is a measure of force, by the way. That's the difference between mass and weight. Weight is actually a measure of force. Area is going up, so the pressure goes down, so the nails don't puncture you. So really, as long as you were to get on the bed of nails carefully, anyone could do this. Now, a person who is lighter would be able to do it on fewer nails, but that's the basic idea. So, when you think about it in terms of gases, if I have a gas trapped in a container, right, these particles, as per the kinetic molecular theory, have kinetic energy. And they're colliding with the walls of the container and with each other, right? So the collision from the kinetic energy, this force, and this is the force that the gas is providing. And if we take that force and divided up over the area of the container, that internal surface area of the container, now we have the pressure. So we're going to talk about, in terms of kinetic molecular theory, what makes the pressure go up or down. And you can probably start thinking of some things that would make the pressure of a gas in a container go up or down. Now, there's also kind of another way to think about pressure. And this is the pressure we experience every day. This is what keeps our insides inside, and this is also kind of why, the idea of your ears popping. The atmosphere, the air that surrounds the Earth, has mass and weight and is attracted to the Earth by a gravitational pull. There's a pressure, a weight of that gas that is on us, and you can think of this as the atmospheric pressure. So everyone is probably, being the Pacific Northwest, everyone is probably familiar, if I have water, right? If I were to dive down under the water, I'm exhibiting, if I'm here, there's a certain amount of pressure from the water pushing down on me. But if I were to dive deeper, there's more water on top of me and therefore more pressure, right? Everybody's probably familiar with this idea of pressure from the water. Well, exactly the same thing is going on in the air around us in our atmosphere, right? Exactly the same thing is going on. If I'm here on the surface of the Earth, right, there's air all up here, and if I'm at the surface of the Earth, I have sort of a maximum of air pressure pushing down on me. But if I were to climb to the top of a mountain, right, there's less pressure. This is why my ears pop, because there's air trapped in your head, and as you go up, the outside pressure becomes less, the pressure inside your head stays the same, and the imbalance, if you have air trapped, if this pressure lessens and this pressure stays the same, you get a net pushing out, and that's why your ears pop. Or if you go from high elevation to low elevation, the opposite is true. So you can think of pressure in two ways, from trapped gas and from atmospheric pressure from sort of the weight of the gas. I mean, the gas is still trapped by the gravitational pull. That's one way to think about it. Okay. One of the most common units of pressure is millimeters of mercury. Another name for this is the torr. Where this comes from is the first person to figure out how to measure barometric pressure was an Italian named Evangelista Torricelli. And this guy took mercury and filled a tube with it. And what happened was the weight of the mercury was pulling down on the tube, on the mercury in the tube. And it only fell so far, right? It stayed up here somehow. And what made it stay up there, what made the mercury stay up there, is that there is pressure from the air pushing down on the outside. So that is what's supporting the pressure is going in this way, and that's what's supporting that column of mercury. And it's simply a matter of the higher the pressure is out here, the higher the column of mercury is on that day, right? If the pressure changes, which it does, that column, the height of the column will be higher or lower depending on whether the pressure is higher or lower. Now, I could do this with water, but the problem is, since water is substantially less dense, I would need a much, much bigger column because the weight of the water is a lot less, but the pressure is the same. So I'm going to need this, the atmospheric pressure would be capable of supporting a much higher volume, or much higher column of water. So I only go through all that explanation to explain where these terms come from. So the reason we use millimeters of mercury is because that is the measurement from the original barometer as millimeters of mercury. It was the height of the mercury column in millimeters. Another name for this unit, and these are interchangeable units, they're the same unit, is the torr, named after the inventor of the barometer, Evangelista Torricelli. So a millimeter of mercury and a torr are the same thing. I will use them interchangeably. I will swap back and forth between them at will. At sea level, the pressure on an average day is 760 torr. So we're a little above sea level here, so it'd be a little less on a given day, but it's about 760 torr. So I want you to understand that the actual atmospheric pressure can change from day to day, right? It's not always 760. It fluctuates. However, because of this average, we have a unit based on the average called the atmosphere, right? So the atmosphere is just a unit of pressure. It is equal to 760 millimeters of mercury or 760 torr, because they're the same unit, right? Well, so be aware that even at sea level, the pressure is not always going to be 1 atmosphere, right? The pressure is going to fluctuate up a little, down a little. On a given day, you could have a pressure of 0.95 atmospheres. Atmospheres, the unit is just a unit, right? It's not saying, we don't recalibrate it. We don't recalibrate the unit every day. Okay. Pressures in millimeters of mercury or torr are always considered to be significant, at least to the ones place. So this is 3 significant figures. Right? Actually, this is going to be an exact conversion factor. But if you see 750 torr, that's 3 significant figures. Right? Okay. So another commonly used unit of pressure is pounds per square inch. This is mostly imperial system. Oh, by the way, I do expect you to memorize this conversion factor. Yes, I do expect you to know 760 millimeters of mercury is 1 atmosphere and vice versa. You don't need to memorize pounds per square inch. I'll give this to you. However, I bring this up a lot of times just to sort of give you the basic idea of what's, just because it's a unit you see a lot. So it's a little, 1 atmosphere is a little less than 15 psi. So if you think about this, there's a couple important things here. So if you have a tire, right, a lot of times tires are inflated to 30 psi or thereabouts. So when you think about it, the way, I'll talk about how you measure it in a second. So this is going to equal about, right, 2 atmospheres. It's about 2 atmospheres, right? Because an atmosphere is about 15 psi. So it's going to be a little less than 2 atmospheres. However, remember, the way this is measured is you have this little valve. Wow, I'm not going to be able to draw this at all. And you put this on the tire valve, and it has a little thing that shoots out. Remember, there's also atmospheric pressure pushing in on this in all directions, right? So really, the pressure in the tire is about 3 atmospheres because we have to account for the other atmosphere of pressure pushing here, right? So it's about 3 atmospheres, really. Okay. So let's talk about gas law variables. So finishing up, so pressure and volume can usually be in any units you want. You just have to be really careful about making units cancel. I will talk specifically about these when we talk about each of the gas laws. Temperature is the big one to be mindful of. Temperature always will be in Kelvin. It's never not in Kelvin. It's always Kelvin. I will explain why it has to be in Kelvin. Let me erase this. Okay. So think about what is temperature a measure of? Temperature is a measure of kinetic energy, right? Well, think about it this way. If I have a temperature of 25 degrees C and then a temperature of 50 degrees C, if I increase it to 50, have I doubled the kinetic energy? The answer is actually no. I have not doubled the kinetic energy. The reason I haven't doubled the kinetic energy could be easily explained by explaining this. This is a 25-degree difference, right? Okay. Well, what about negative 10 degrees C and 15 degrees C, right? So here's the problem. The problem is that we are using a scale that's got a 0 smack in the middle of it, right? This is problematic because obviously if we're going to be measuring kinetic energy, if I need to have a temperature so that if I double the temperature, I'm doubling kinetic energy, which means they must both have the same 0 point. 0 kinetic energy must be 0 on the scale. Now, there is a temperature unit where this is true, and the answer is that's Kelvin. So because we're very carefully tracking kinetic energy, we have to use Kelvin because Kelvin is scaled appropriately with kinetic energy where Celsius is not, because 0 degrees Celsius is not 0 kinetic energy, right? So we have to use Kelvin every single time.